Once again, this is Arvind Krishnan at GoEngineer, and today we are going to talk about topology optimization using SolidThinking Inspire. So once again, just a quick introduction of what topology optimization is. It's always been the central theme of engineering to reduce the mass of your designs as much as possible. And if you look at any design or any bracket, the primary focus of that is to transfer a point of loading to a point of fixture. If you imagine that point of loading on the left is point A and the fixture is point B, the lines that you see, the solid lines in the middle, are lines that kind of combine those two together. And the best or the most optimum way to do that is to place material along what's called the alpha and beta lines. The lines on the top are the ones that kind of go like this are going to be in tension, and the lines that go like this are going to be in compression. And these two intersect at 90-degree angles. And if we draw a neutral axis that joins point A and B, you're going to notice that all of these lines combine them at 45-degree angles. This was the work of Dr. A.G. Mitchell back in 1904. And thankfully, now we have software that does a lot of this. So if we took that same example, went to a problem that's pretty well known in the industry, a cantilever beam, and added a load and at the blue dot on the left, and our right side was fixed, then that would be the most optimum shape. So topology optimization is the regions in your model that you need to keep to get the stiffest structure, the most bang for your buck, in a way, to say where the material that you keep is contributing the most to the stiffness of the design. Once again, there's a multitude of applications ranging from architecture, buildings, aerospace, automobile, brackets that you see in the bottom middle, which is some of these are conducive to 3D printing, whereas others, like the rotary application on the right, can be machined. The buildings on the left are typically going to be weldments, but it's where you want to place those weldments that can be optimized as well. Okay, so today we're going to look at this truck. This is a truck of a colleague of mine, and it actually just sits right outside the office where we are located here in Dallas. And if you notice this one region, the stepping, this step region, you see this little bracket here, and that's what I'm going to work with today. So we're going to take that bracket and we're going to see if we can apply some topology optimization to that. You see the two big round holes in the middle, so obviously there's some weight reduction that has been tried, but is there a better way to do this? So what we're going to do is we take that initial design, and I'm going to first create a SOLIDWORKS model out of it, right? Something relatively the same, because I'm looking at what is the best design that I can get. But I'm still in the initial conceptualization phase, so I'm not looking for something exact. And then we take that design and we go ahead and bring it into SolidThinking. And I'm going to show you how I do this, but basically the first step is to create what's called my design space, the region that can be optimized and weight can be removed from. Once we do that, we can then go ahead and describe our different loading conditions, describe where this is fixed, what is, imagine someone stepping in the middle, what sort of loading condition that creates. Imagine someone bumps into it, right? That's what this side load is. What happens then? And we're basically going to optimize the shape of this bracket based on the loading conditions that are applied on it, which, now that you think about it, seems very trivial in that you want to optimize your designs for whatever loading conditions are there, right? And that's what we're going to do. Only thing, we're going to take the help of a software to do that. And what it does behind the scenes is it's using something very similar to a bone growth algorithm, and it finds the best shape to get from the point of fixture to the point of loading. Okay. So solid thinking has 4 different types of optimizations available. The first one is topology optimization, which we're going to look at today. Okay. What it does here is the regions that you see in kind of dark red maroon is the regions that it recommends you to keep based on a given loading condition and fixture. And then other regions it kind of recommends you to remove that. You also have topography applications or topography optimization. And I typically like to describe this as an optimized rib structure, right? Where do you want to place your ribs to get the stiffest structure possible? The one other way that I like to distinguish the two is in topography optimization, you can get watertight models. Your models continue to stay watertight. Whereas in topology, that's not the case. You actually have holes in the middle. Then you have gauge optimization. And in gauge optimization, think of a sheet metal application where you're looking at what's the minimum thickness I need to make sure that this part is going to work for whatever application it has. You also have the ability to combine topography and gauge. So imagine a thin shell feature that can then be optimized for thickness and the placement of the ribs. And lastly, we have lattice structure creations, where you're creating internal lattices, and it's going to add thicker lattices, as we can see on these regions on the top, whereas you have relatively thinner lattices in other regions where there is not as much stress produced. You can also combine topology and lattice optimization, so that's another good benefit. Okay, so that's some of the theory behind SolidThinking Inspire and topology optimization. Let's go ahead and get started and look at SolidThinking Inspire. So I'm going to take you through the entire process. So I'm going to just go ahead and bring in a SolidWorks part, right? And this is how I had it modeled. Very simple model, nothing too complicated. And the first thing I'm going to do is I'm going to create that design space. So there's a nice partition tool that helps me define regions that I need to partition out because they're not going to be part of the design space. Okay, so with a couple of clicks, what I just did was I divided my body into 3 parts. That's the first one, which I just hid, and then these are the second ones that is going to be part of my final shape. Okay, so this body in the middle is going to be what we call our design space. That design space is what is going to be used and material is going to be removed from it. Okay, now that I've done that, I can do a bunch of other modeling changes as well, and we will revisit this towards the end of the webinar to create our final shape. But let's go ahead and look at defining the rest of my load-based optimization study. I need my material, so all of these parts are going to be 70-75 aluminum. I also need fixtures, right? So that's going to be fixed, and I need my loading conditions. So I'm going to add a load on this face, and I want it to be pointing downward, and imagine a 400-pound person stamping on this, so half the load is going to be 200 pounds. But the only difference is the load is not going to be on this region. So first off, direction of the loading is in the Y and negative. We're actually going to move this load away so that it's slightly away. So if the entire bracket leg space was about 6 inches, half of that would be 3 inches. Right? So what this does is you're actually going to see a moment being generated on this structure because that load is offset by a certain amount. So you do have the option to offset that load to create a more realistic loading condition scenario. Okay, so that's that load. I can add multiple load cases if I want. So you don't expect a person to be standing and this bracket to be hit at the same time. So we can add a second load case only on this face and create 2 load case scenarios. Okay, so that's possible as well. And then for the next step, I'm going to make sure that I specify how this is going to be manufactured. Okay, so once again, topology optimization has been doing a lot of the rounds of late, and very often it's been used in conjunction with 3D printing. Conversations of both of them happen at the same time, but that need not be the case. You can have a topology optimization study run on parts that you're going to machine, that you're going to cast, that's going to be molded. So in this case, I'm going to do a single draw, and I'm going to specify that this is the direction that I'm going to draw that part, right? And what that does is it defines the shape such that the cross section it has is relatively constant, so that my mold can actually come out, or the forming tool can actually come out, and I can create all the internal regions. Something new that was added in 2018 for SolidThinking is this overhang tool. For those who are actually using topology optimization in conjunction with 3D printing, the time it takes to 3D print something is heavily dependent on the amount of support material you have. So what that overhang constraint does is it lets you input, let's say, a 45-degree angle constraint, which means anything below 45 degrees would need support below it. So that overhang constraint is going to try to keep all of the internal regions above a 45-degree angle to the horizontal. And if you go ahead and 3D print that, you're going to see an exponential reduction in the time taken to print it. So very useful tool. Okay. So single draw method is what we are going to use. And once you select that axis, we've specified our fixtures, we've specified our materials, we've specified the manufacturing method, and we've also specified our loading conditions, right? So next up, we can go ahead and run this optimization, right? So I can go ahead and hit the magic run button. And this study takes about 5 minutes to run, so I've saved another model with the run already done. But I want to talk about a few of the options available here. So first off, we spoke about combining different types of optimization methods. So here's your topology, topography, gauge optimization, combining the rib structure and sheet metal thickness into one, or the lattice structure optimization, right? Just FYI, we have a bunch of webinars in our YouTube channel that covers a lot of these. So please do go and check it out if you're interested in the others. Right now, I'm going to select topology. The next question is, how much of the mass do you want to keep, or rather, how much do you want Inspire to remove? So if I click on 40%, then it's going to try to remove 60% of the mass. I can also include frequency constraints. That seems important. I need to, if I have a resonant frequency limit for any aerospace applications or automobile applications, any sort of dynamical systems, that's going to be very useful, where you can specify the lower limit of the frequency. And lastly, the thickness constraint. Think of this as your mesh size. You can specify what mesh size you want, and that's what the elements are going to be. For those who've done FEA before, there is a faster or a draft quality mesh, and there's also a more accurate or a high quality element analysis that you can do, which takes slightly longer to run. So yeah, typically at this time I would run this analysis, but I have gone ahead and already done that beforehand. So let me go ahead and show you some results. All right, so this was my initial part. And once I go ahead and run it, this is the optimization results it gives me. Okay, so if I go ahead and look at this little dialog box here, I can take the slider to the left, which reduces the amount of material. So as I take the slider to the right, it's keeping material that is in the most important regions that contribute the most to the stiffness. Okay, and to anyone looking at this the first time, the typical question that pops up is, why is there a slider? Why do I have to select how much material I want to keep or not? And to answer that, what I would say is this is showing you the regions that contribute the most to the stiffness, but we haven't actually ran an analysis to know if this works or not. So typically a topology study is is followed up by another FEA analysis, like a linear static analysis that looks at what the stress limits are, whether I'm within my bounds, if I need to go thicker or thinner. So that's what the slider is for. Now, very often the question about topology tools is, what do you actually do with these results? Because what you're seeing on your screen is just a graphical result. And Inspire has a tool called the Polynurbs tool, which actually uses these results to create some feedback and lets you create your final geometry. So let's go ahead and do that right now. The wrap tool is very similar to a loft command in some of the CAD tools that we have been using. I'm just going to come in here and click on the different regions, and this is going to help me create geometry that I can then use as a Parasolid file. Okay, so I'm just literally clicking on different cross sections, and that is helping me create some geometry based on the final results. Okay, so I'm just going to go through this, and that's kind of my first step of lofts. Okay, and I'm going to continue using the wrap tool, and this time I'm going to create this extended section here. All right, so go through the cross sections and define another region here, right? And we'll get to kind of bridging that towards the end in just a little bit. I want to create another section on this side. Right, so go through and just literally click and drag and across the different cross sections once I'm happy with it. So now next up, you see that if I kind of merge these two together, there's a pretty big section here, whereas the results are just telling me to merge this much. So that's where the split command comes in, but I can actually split this face and split the different regions. So one click, and now I have actually two selectable regions. And I basically want to bridge these two together. So I'm going to use the bridge command to then select and then select the second face as well. And that creates a bridge. I'm going to do the same bridge tool over here. And that takes care of that. Okay. So once again, with just a couple of clicks, you see that I'm close to my final shape. There's still regions where I've not kind of gone through the other part, so let's go ahead and take care of that next. This is where I like to use the create command, where I just basically pick a face, and then I can just go ahead and extrude in that direction, right? And typically with this, I'm trying to go a little bit further than what I'm supposed to, and we'll talk about merging the two together in just a little bit. Okay, I can also use the plus command, which basically just adds some more material in the same direction that the face was facing, right? So here's another plus, and for this one, I'm going to go back to my create tool, and on this face, I'm going to make a slight change here. I'm going to change that angle so that it faces a little bit inward. Okay, and then I'm going to go ahead and drag this in that direction. Okay, so once again, I can do a little bit more to get this to conform to the final region, but let's assume that this is our final shape for now. There is some sharpening tools available to us. There's also a fit command, and I've done a webinar that talks in detail about Polynurbs, so please do feel free to check that out if you want, which is actually done on the same model, so it would be relatable for you guys. So now the next question is, what do I do with these additional regions that are popping out? And for those CAD users who've kind of used the Boolean operation before, this would be familiar, but for the rest of us, what we're going to do is I'm going to first create a copy of these two regions. So literally hitting Control-C, Control-V on my screen, and that creates another copy. And I'm going to do the same thing on the other side. So Control-C, Control-V, and I'm going to hide my original parts. And now I just have these two copies here, and I'm going to go back to my geometry modification tools. So here's a nice push-pull tool that I can literally just click on faces and drag, and it kind of modifies the geometry of it, right? It's super simple, super easy to use. And as some of you would have estimated, you can kind of think of what the next step is. Let's go ahead and hide my initial results. And now that I've done this, the next step is going to be a Boolean operation. So I'm going to go ahead and do a subtract, where this is my target and my tool is going to be on one side. And then I say I don't need to keep the tools, so I'm going to keep that unchecked and hit subtract. And that's the first side. Let's go ahead and do the same thing on the other side. Select my target, select the tool, and once again I'm going to hit subtract, and it gets rid of the regions that I don't want. Now I can unhide the two components that I had hidden, and there is my new final topology optimized shape that I can use or that I can then build upon. So that's that. Let's go ahead and switch back to the PowerPoint. So that was my initial design, right, where just a couple of holes were added in the middle to supposedly lightweight the design. And then what I did was I went ahead and added some loading conditions. I went ahead and added some fixtures. I specified the material, and that's the final shape that I got that I could then optimize. And finally, I could also create some geometry based out of that. The good thing is I can use this geometry to then save it as a Parasolid. I can go ahead and save it as an STL and 3D print it. So I've actually printed a couple of these in Ultim in my office here, and it looks pretty cool. It's pretty sturdy and a good functional part. I would have to add those ridges to ensure that the top circle does not rotate. But that was a quick introduction to Inspire and the workflow that Inspire does. Some of the options inside Inspire, like topology, topography, lattice, gauge, and how some of those combine. And I do want to add one final thing, that the design on the right that you see, they have to still be analyzed, and we can do that inside Inspire as well. You can analyze it, make sure that the factor of safety is good, that it's a part that where the minimum frequency, the first natural frequency, is above or higher than a threshold limit that you set. All of that can be done inside the same interface before you export the model as, let's say, a Parasolid file. So on that note, I want to say thank you to our audience for listening in.